Good morning, everyone. I'm Praveena, Assistant Professor from AC Department. I'm going to handle RF transceiver, that is vertical subject for you. Okay? That is RF transceiver. RF transceiver is nothing but that is a transceiver is a combination of both a transmitter and a receiver. Okay? I have to work work hard for the subject, right? So it is very easy subject. If you work it daily, you can achieve it good grades. Work hard in your studies today so that your degree certificate tomorrow carries not just your name, but the honor of your excellence. Study while others are sleeping, work while others are laughing, prepare while others are playing, and you will succeed one day. You have to you have to remember these quotes. Okay. Then let us go into the subject. Okay. First, RF transceiver. RF transceiver is nothing but it's an electronic device that combines both the transmitter and the receiver into a single system, that enabling the two-way wireless communication using radio waves. Basic concept is that is transceiver. Transceiver is a transmitter and receiver. Okay. It is widely used in communication system where signals will be sent to the transmitter, right? So, um, the receiver side, the signals will be received to an end. That is a transmitter and receiver. It's a combination of both the transmitter and receiver is a transceiver. Okay. First, the RF transceiver. What is the main function of RF transceiver? First, it converts the baseband signal into RF signals. Baseband signal into RF signal for transmission and converts that RF signals that is received RF signals into a baseband signal for processing. This enables a full duplex or half duplex communication. Then, in RF transceiver, there will be some blocks that is main important for the RF transceiver. What are they? First is transmitter section and receiver section. In between, there will be some blocks are there. First is modulator. Modulator, mixture, power amplifier, and these all comes under the transmitter side. And in the receiver side, low noise amplifier, mixer, and filter. And last is demodulator. Okay. First, the input signal is modulated and it is converted into the RF frequency. The signal is amplified and transmitted via the antenna. So the incoming RF signals are captured by the antenna. The receiver down converts the RF signal into baseband signal for decoding. Okay. Some of the types of RF transceivers are that is you have already learned about heterodyne transceiver, right? So some of the types there are the three types. First is heterodyne transceiver, second is direct conversion transceiver, and third is low IF transceiver. Okay. Where the RF transceivers are used is, let us see the application. First is mobile phone. In 4G or 5G mobile phones and Wi-Fi routers, Bluetooth devices, satellite communication, etc. Then these are the topics that comes under the unit. Unit one topic is CMOS physics, transceiver specification, and architecture. Okay. In this unit, it gives about an overview of the fundamental concept that is used in the RF CMOS transceiver design. It begins with the introduction of CMOS technology and MOSFET physics. It explains how the MOSFET devices are operating and it forms the basis of integrated RF circuits. And it also covers various noise sources in electronics that includes thermal noise, short noise, flicker noise, popcorn noise, which affect the signal quality and receiver performance. The important transceiver specifications such as two-port noise theory, noise figure, total harmonic distortion, and second order and third order interceptor points, receiver sensitivity, and SFDR. SFDR is the spurious free dynamic range are discussed to evaluate a system, overall system, that is a RF system performance. And finally, the unit covers it, the common transceiver architecture, that is heterodyne, homodine, heterodyne, image reject, and low IF receiver, um, that is a up conversion, down conversion, and highlighting their operation principles, advantages, and applications of the wireless communication system. Let us discuss it briefly. Okay. First, introduction to the MOSFET physics. What is mean by generally? What is mean by MOSFET? MOSFET is nothing but it is a metal oxide semiconductor field of the transistor, right? You have already learned it in electronic devices, right? So it is a voltage controlled semiconductor device, and it consisting of four terminals. What are they? That is gate, source, and drain, and substrate. That is a body, and we are not considering the substrate. GDS. I will remind that the gate is insulated from the semiconductor channel by a thin oxide layer, right? So by applying a voltage to the gate, the conductive channel is formed between source and drain. This allows the current to flow. So generally, the MOSFET are widely used in CMOS integrated circuits due to the low power consumptions and high switching speeds. And, the body effect. The body effect refers to the change in the threshold voltage. That is due to the voltage difference between substrate and the source terminal. And when the voltage between the source to body increases, that is source to substrate increases, the threshold also increases. So it is make harder to turn on the transistor. So this effect is very important in analog and RF circuit design because it helps to calculate the overall performance of the system. Then is channel length modulation. Channel length modulation is basically occurs in the saturation region when an increase in source drain to source voltage. It causes a effective channel length to decrease. So, as a result, the drain current is slightly increases instead of remaining constant. So this phenomenon is similar to that of early effect in BJT, and BJT is nothing but bipolar junction transistor, and it causes the MOSFET to exhibit outer resistance, which affects the amplifier gain and analog circuit performance. Let us see the MOSFET structure. This is a MOSFET structure, NMOS structure, that is the left side, and built on P type substrate, that is a source and drain are heavily doped in region. That is gate is placed above the thin silicon dioxide insulating layer, and body, that is B, is connected to the P substrate. When a positive voltage is applied to the gate, that is when a positive voltage is applied to the gate, that is a channel forms between source and drain, right? That is N channel that is formed between source and drain. So then PMOS structure, that is the right side, and that is built inside an N well that is formed in the P substrate, right? So source and drain are heavily doped P plus region, that is P region, and body, that is substrate, is connected to the N region, N well. So negative gate voltage is applied. The P channel forms between source and drain. Okay, this allows the current to flow. What are they? There are four terminals in a MOSFET. What are they? Gate, drain, source, and substrate. Okay. First, terminals. Let us see the terminals. Okay. Gate. The gate generally controls the transistor combination. And the source on the it supplies the charge carriers. And the drain is used to collect the charge carriers. Source is used to supply the charge carriers, and drain is used to collect the charge carriers. The body or substrate that forms a transistor body and affects the threshold voltage. Okay. Why NMOS and PMOS are used together? In CMOS circuit, that is NMOS resistor transistors are good at pulling the output flow, and PMOS transistors are good at pulling the output ahead. So only one transistor conducts significantly at a time, that results in a low power consumption. Okay, let us see the MOSFET structure. And NMOS and PMOS are fabricated in a lightly doped silicon substrate. That is with the source drain gate and substrate terminals forming the basic and MOSFET structures. Okay. This the thin silicon dioxide insulating layer separates the gate from the substrate. Substrating, that is a thin silicon dioxide insulating layer that separates the gate from the substrate, that are allowing the gate voltage to control the current flow between source and drain. Okay. Next is in NMOS transistor, that is source and drain are formed by heavily head-doped region with a p-type substrate that are physically identical and making them interchangeable. So the body terminal is heavily p-doped and provides a good electrical connection to the substrate that helps to control the transistor operation. So next is MOSFET structure. MOSFET structure, that is, I have already told that the NMOS transistor is heavily head-doped source and drain region that is formed in a p-type substrate, and both the terminals are physically identical. So heavily p-doped body terminal that provides a reliable connection to the substrate and influences the transistor electrical characteristics. And let us see about substrate sub-threshold connection, MOS device layout, MOS device capacitance, and MOS signal mode. MOS threshold connection. That is, it is nothing but it's a small drain current that flows when a gate to source voltage is below the gate. It is nothing but threshold voltage. It is also called a weak inversion region. What is called? It is called weak inversion region. So in this region, the current fully depends exponentially on the gate voltage, making it a leakage source in a digital circuit, but it is very useful for low power application, ultra low power application. It is nothing but it is a small drain current that is flows when the drain gate to source voltage is below the threshold. Okay, that is called a weak inversion region. Next, we are going to see about MOS device layout. MOS device layout is the physical arrangement of MOS transistor under interconnection on a semiconductor chip. Okay, MOS layout is nothing but that's a physical arrangement of MOS transistors and interconnections on a semiconductor chip. Okay, it defines the placement, size, connections of a transistor to implement specific functions in integrated circuits. Then key components and concepts in MOS device layout. Nothing but that is MOS transistors with the basic building blocks of MOS circuit. It consists of what are they? There are the four terminals. What are they? Gate, source, gate, drain, source, and substrate. Okay. And it can be either, there are the two types. It can be either NMOS or PMOS. The diffusion regions are doped semiconductor, that is a doped semiconductor areas that form source and drain terminals that are enabling the current that flows to the transistor. Then let us see about the metal layers. The metal layers are used to create a reliable interconnection and power distribution networks between the different components of the chip. It's used to create a reliable interconnection and power distribution. Metal layers and active region, it is used to create reliable interconnection and power distribution network between different components in a chip. Okay. The active region is the area where the NMOS, that is the MOS transistors are formed, created by the overlap of diffusion region and gate polysilicon. So next is key aspects of MOS device layout. Transistor structure, that is a MOS transistors. MOS transistors are the basic building block of integrated circuit. You all know about it, right? So MOS transistors are the basic building block of integrated circuit. It consists of four terminals, and the MOS layout specifies the physical size, shape, and placement of these terminals and the surrounding regions of the chip. Then layers. Layers are or the MOS circuits are fabricated using a layers of diffusion, right? So either N-type or P-type. So that is a polysilicon and metal that is also to form a transistors and interconnection. These layers are separated by thin and thick silicon dioxide insulating layer in order to ensure the proper electrical isolation and operation. Then active regions. Active regions are the areas on a chip where the MOS transistors are formed defined by tin oxide region and polysilicon gates. Contact is nothing but it's an electrical connection between transistors and transistor terminals and other circuit layers using a metal or polysilicon interconnects. Then, then we are going to then we are going to see about design rules and parasitic capacitance. That is, the layout design follows a specific design rules for minimum dimension and spacing in order to prevent a short circuit. This ensures the reliable operations and maximum chip density. Um, and parasitic capacitance. Parasitic capacitance between the layers and terminals can affect the circuit performance and minimize due to careful layout design. If you are designing a layout, so we have to be careful while designing the circuit. Okay. MOS device capacitance. Next is. So MOS device capacitance arises from the gate oxide layer and channel structures of MOS transistors. These capacitance affect these capacitance, that is a parasitic MOS device capacitance. This affects the switching speed, signal propagation, and overall circuit performance. This makes making them important in MOS circuit design. Then types of MOS capacitance. That is a gate capacitance. Gate capacitance is a primary capacitance as MOS device. That is main capacitance. That is formed between the gate electrode and channel to the oxide layer. It is a voltage dependent. That is a gate capacitance is a voltage dependent capacitance. Meaning is that it changes with the applied gate voltage and operating conditions of the transistor. It changes with the applied gate voltage and operating conditions of the transistor. Then gate to source capacitance. Gate to source capacitance, that is CGS, that exists between gate and the source. From the notation itself, we can guess that is the capacitance that exists between gate to source, right? So while gate to drain capacitance exists between gate and drain terminals. So drain to source capacitance is a parasitic capacitance that exists between drain and source terminal. That will affect the switching speed and circuit performance. So let us see the factors affecting a MOS capacitance. That is, these are the factors, that is oxide thickness, channel length, and the doping concentrations and applied voltage. Factors affecting, that is, MOS devices capacitance are influenced by oxide thickness, channel length, and the doping concentrations in the semiconductor region. The applied voltage also affects the capacitance value by changing the charge distributions and operating regions of MOS transistor. So, MOS signal model, that is the small signal MOSFET model. The small signal MOSFET model represents transistor behavior. It's nothing. It represents a transistor behavior for small variations around its operating point. Okay, it will simplify the circuit analysis and it linearizes the MOSFET characteristics, and it is widely used in amplifier design in order to analyze voltage gain, current gain, and frequency response. So noise. These are the noise. What are they? Thermal noise, flicker noise, and compound noise. First is thermal noise. Thermal noise is nothing but it is caused by the random motions of electrons within a conductor due to the thermal energy, even when there is no current is flowing. Okay. Now, this random electron movement produces a small voltage fluctuations across the resistor, and it is also called a Johnson-Nyquist noise. It is nothing but it is a random motion of electrons within a conductor due to the thermal energy. So even when there is no current flow also, there will be some random motions of electrons. Okay, so that will produce some voltage fluctuations across the resistor. That is called a Johnson-Nyquist noise. It's also called a thermal noise. Due to the overview is that due to the thermal energy, there will be some electron movements in the conductor. So that will leads to some voltage fluctuations around the resistor. That is known as Johnson-Nyquist noise. Okay. Then Generally, the MOS transistors also exhibit the thermal noise, which is generated by the random motion of charge carriers in a channel region. Okay. For a long channel MOSFET operating in a saturation region, this channel noise is modeled as a noise current source connected between drain and source terminal. Then is flicker noise. Flicker noise is also known as 1 by F noise. It's a dominant low frequency noise in a MOSFET. This increases as the operating frequency increases. It is mainly caused by the trapping and re-trapping of charge carriers at deflects near the silicon oxide interface. Yeah, this results in a current fluctuation. So, flicker noise, let us see the overview. The flicker noise is otherwise called a 1 by F noise. It is mainly, yes, when it is mainly in the MOSFET. So that increases as the operating frequency decreases. So it is mainly caused by trapping and retrapping of charge carriers at deflects near the silicon oxide interface. So this results in a current fluctuation. So next we are going to see about the popcorn noise. Popcorn noise is nothing but it's a burst noise or random telegraph noise. Okay, it's a low frequency noise. So popcorn noise is known as burst noise or random telegraph noise. So it's a low frequency noise. It is mainly observed in the MOSFET and other semiconductor devices also. It appears as sudden or random jumps in voltage or current levels, produces a popping effect that resembles a popcorn. So what is that? Uh, so when near to the speaker, it resembles a popcorn when near to the speaker. Okay. What what are the noises we have seen? First is thermal noise. Thermal noise is due to the movement of movement of electrons. Due to the thermal energy, there will be some movement of electrons within a conductor that will lead to the voltage fluctuation. That is a thermal noise. And what is meant by flicker noise? And flicker noise is otherwise called as 1 by F noise. That is, it is mostly common in MOSFET and semiconductor devices. It will increases as our operating frequency decreases. Okay, it is mainly caused by trapping and pre-trapping of charge carriers. It results in a current fluctuation. So next is popcorn. Popcorn noise is otherwise called as burst noise or random telegraph noise. That is a RTN, random telegraph noise. It's a low frequency noise. It is mainly observed in MOSFET and other semiconductor devices. So it will appear as sudden or random jumps in voltage or so it's like a popcorn. So it resembles a popcorn when near to the speaker. So these are the noises we have. Next is two-port noise theory. Two-port noise theory is nothing but it's generally used in RF and microwave circuits in order to analyze the noise behavior of two-port network, such as amplifiers, mixers, and filters. Generally, for two-port network, there will be the four S parameters. What are they? First is S11, S12, S21, and S2. Let us briefly discuss in second unit. Okay. Let us see the overview of our two-port noise theory. Okay. Two-port noise theory is generally used in RF and microwave circuits in order to analyze the noise behavior of two-port networks, such as amplifiers, mixers, and filters. It helps to determine how much noise a device adds to a signal and evaluates the impact on overall performance of the communication system. So, that is a two-port network has two pairs of terminals. That is an input port and output port. That is a port 1 and port 2. And the port 1 is, these ports are mainly used to model the RF components, such as LNA. LNA is nothing but low noise amplifier. What is the main function of amplifier? Means it's used to amplify the beat signal. Okay? Right? So mixtures and filters. So what is the use of filters? So use it to remove the unwanted noise. There will be many types of filter. That is a low pass filter, high pass filter, band pass filter, and band stop filter. That is what is the use of low pass filter? Low pass filter. It allows only the low range of frequency and it blocks a high range of frequency. And according to the port condition, that is a current entering to the one port one terminal of the port, it must be equal to the current leaving the other terminal of the same port. That must be equal. For entering current, leaving current, it must be equal. Okay. Then is noise figure. Noise figure is nothing but it is a measure how much a transceiver, that is amplifier, or how much a transceiver or amplifier or other RF devices that degrades SNR. SNR is a signal to noise ratio of an input signal. Okay, that is a noise figure, and it indicates how much a component that is had noise to the signal, and and impacting the receiver ability in order to detect the beats. Okay. Next is total harmonic distortion. Total harmonic distortion is that it's nothing but it measures the deviations of RF signal from its ideal form due to the harmonic distortion caused by system non-linearities. It is a very important parameter for evaluating the transceiver linearity and indicates the amount of unwanted harmonic components present in the transmitter and receiver signal. Okay. Next is IP2. IP2 is nothing but that is a second order intercept point. IP is an intercept point, second order intercept point. Okay. So then it's a measure of system's ability. It is nothing but it is a measure of the system's ability to withstand the second order nonlinear distortion and indicates the input power level where the extrapolated distortion power equals the desired signal power. Distortion power is equal to the desired signal power. So it is especially important in the horror system that is operating in the environment in the strong in-band and out-of-band interference circuit. Next, we are going to see about IP3. IP3 is nothing but third order interceptor. It is also a measure of transceiver ability in order to tolerate the third order intermodulation distortion, and it represents the input power level where the third order distortion products will be equal to the desired signal power. So it is very critical in a multi-signal environment. Okay. So as third order intermodulation products can create the interference and degrade the overall system. So next is sensitivity. These are the factors we have to consider while designing a system, RF system. So sensitivity. Sensitivity is the minimum input signal power that a receiver can detect while maintaining a specific SNR and the acceptable error rate, such as a BER. BER is known as bit error rate. Okay, so in the digital system, it directly affects the communication range and reliability of an RF receiver, especially when receiving a weak signal in low power environment. So next is spurious-free dynamic range, that is ST-SFDR. It's a range of input signal powers over which a transceiver can operate without exiting the noise flow or the desired signal. It indicates the dynamic range of the transceiver and its ability to handle both the weak and strong signals simultaneously without any distortion. Next is phase noise. Phase noise is nothing but it's a measure of short term of a signal phase or a frequency over a time. Then we have to consider these parameters. Yes, phase noise is a instability of a signal phase or frequency over a time. It is essentially the frequency domain representations of random fluctuations of a signal or a wave. Then signal integrity. The phase noise refers to that is unwanted random fluctuation in the phase of a signal, which degrades the signal integrity and causes error in the data transmission and measure. Generally, in communication system, that is a high phase noise reduces its overall system performance by increasing the error rates and lowering the data rates, and it will leads to some performance. It will affect the system performance. So we have to consider these parameters, right? So in radar system, the phase noise can reduces the ability to detect the weak targets, and it can distort the accuracy of the received radar. Just it is also important measure of oscillator stability, since low phase noise indicates a more stable and reliable frequency source in electronic system. So next is that is signal integrity, system performance, radar system, and oscillator stability. And phase noise. Phase noise is that is this circuit shows that is a parallel RLC network. It is resistor, capacitor, and inductor. So that is connected to a block called noiseless energy restorer. It represents that system where the losses in RLC circuit are compensated by restoring the energy without adding noises. Is it clear? It represents in the system where losses in RLC, that is RLC, will be connected in parallel, right? So if there is any losses in the RLC circuit, that will be compensated by restoring the energy without any adding any noise. And it will maintain a sustainable oscillation. So this is a graph. And these are the expressions we have to remember. And this is a graph between high bias and that is voltage and the current. Okay, bias in current and oscillator voltage. That is the current will be limited and voltage will be limited. We have to remember this. That is the radio transmitter that will convert the low frequency baseband signal to a high frequency baseband signal by modulating the sine wave carrier with the information signal. The modulation can be achieved by varying the amplitude, frequency, or phase of a signal carrier in order to produce a modulated signal for transmission. Let us see the transceiver architecture and receiver. That is, in urban wireless environment, that is called an hostile environment, because the signal faces a multi-path feeding, interference, noise, and obstruction from the buildings and moving object, right? So that is, there will be the limited bandwidth per user. Further constraints the RF transceiver design requiring a high selectivity, efficiency, and interference rejection. So this is a diagram. This shows that the transmitter side, that is a power amplifier that will boost the signal, and band pass transmitters, that is a power amplifier, will boost the signal, and band pass filter removes unwanted noises, and before the antenna transmits the received signal, it will reduces the adjacent channel interference, and at the receiver side, the antenna receives the received signal along with the strong interference, and BPF, that is a band pass filter that will select the desired channel, and the LN is a low noise amplifier that will amplify it while minimizing the noises. So it overall, it will explain how filtering and amplifications helps in maintaining the signal quality in a noisy environment. So transceiver architecture and receiver. So here is the narrowband modulation. The narrowband modulation uses a stick bandwidth control along with amplifications and filtering in order to prevent the signal leakage into the adjacent channel, ensuring that the receiver receives a desired signal. Okay. In order to achieve the high selectivity, that is a very short filters are required. For example, second order LC filter needs 60 dB attenuation at 45-degree growths. So, if you require a high quality, that is a high Q factor, which is impractical even with the advanced SAW filter technology. SAW is nothing but surface acoustic wave. So, next is third order nonlinear distortion. Third order nonlinear distortion is the most critical because it creates a unwanted intermodulation products that is closer to the desired signal. So each stage must have IIP3. That is a IIP3 is nothing but intercept point. IP is nothing but intercept point, third order intercept point in order to maintain a signal purity. So next we are going to see about heterodyne receiver. Heterodyne receiver is also otherwise called as super heterodyne receiver. That is nothing but it converts, that is, this receiver will convert the incoming RF signal into the IF signal by mixing it with the local oscillator. The wait, I'll see the block diagram. Here, the higher frequency will be coming. So it converts the incoming RF signal will be coming and it will be mixed with the local oscillator frequency. So IF signal will be coming and it will be mixing with the RF, so IF frequency. That mixing will be takes place with the local oscillator. Okay. The mixture produces a beat frequency, that is the difference between IF frequency and local oscillator frequency, which is selected as a higher. This makes it easier to filter, amplify, and process the signal for better stability and performance. That is the signal RF signal, that is omega 1 will be, that is an incoming signal, centered at W1. The incoming RF signal is centered at W1, that is a reset signal band, is fed into the mixture along with the local oscillator, that is a L, that is A naught cos omega naught T. The mixture produces a two frequency component, that is omega 1 plus omega naught plus omega 1 minus omega naught. And it will be processed to the low pass filter that will remove the high frequency component and it keeps a difference frequency. The output becomes a shifted version of the signal. Okay. And next is, that is, I have already explained. So in a super heterodyne receiver, that is a local oscillator can sit either above or below the received signal band center frequency, such as known as high side injection. That is local oscillator above RF frequency, and low side injection is that local oscillator below RF frequency. In a dual IF topology, that is where there is a trade-off. The two intermediate frequencies are used in order to overcome the limitations of single IF design. In a simple heterodyne receiver, there is a trade-off between sensitivity and selectivity. So if a high IF is chosen, the image frequency rejections improves, but channel filtering becomes very difficult. So if you chosen a low IF base, channel selectivity becomes improves, but image rejection becomes very poor. So we are going for a dual IF. Dual IF architecture balances this by using first IF for image suppressions and the lower second IF for better channel selectivity. So there will be the two stages in dual IF topology. Okay. So the narrow channel standard suggests IS54, the second intermediate frequency. IF is typically around 455 kilohertz. Then, due to the excellent selectivity and sensitivity, the heterodyne architectures have remained the dominant choice in RF receiver system for so many years, for many decades. Next is homodyne receiver. Homodyne receiver is a local oscillator frequency is set equal to the input carrier frequency, so that signal is directly converted to baseband. Okay. In this architecture, that is resonance selection can be achieved using low pass filter with relatively short characteristics instead of complex IF filtering stages. So that will be the two advantages. What are they? The image frequency problem is completely avoided, and in additional sense, RF is directly converted to the baseband. In let us see the overview. In homodine receiver, that is the local oscillator frequency is equal to the input carrier frequency. Local oscillator frequency is equal to the input carrier frequency, so that signal will be directly converted to the baseband. So this is the main concept. and channel selection, that is rejection of a stronger out of band interference using a active low pass filter. It is more difficult compared to the passive filters. So this is because the active filters involve amplifying devices which introduces in the noise, non-linearity, and power consumption. So as a result, the designing an active low pass filters requires careful balancing of performance parameters. So DC offsets. DC offsets, that is in a direct conversion receiver, some of the local oscillator signal leaks into the input and mixture and mixes with the mixture with itself. So this causes an unwanted DC signal called self-mixing that will be mixed by itself. So the problem is that by removing the sorry the direct conversion. So in a direct conversion receiver, some of the local oscillator signals will be leaks into the input and mixes it itself. So it is called a self-mixing. I've already told that, right? So next is IQ mismatch. IQ is nothing but that is in a heterodyne receiver, that is a IQ down conversion can be used. That is the matching record high and Q bar are not very strict. Earlier, the IQ mismatch is a big problem in a discrete design. But now with the monolithic integration, the issue is reducing because both I and Q circuits are built together more accurately and making the monodite and architecture more practical. Next is next is Hartley architecture. So Hartley architecture. Hartley receiver is a very popular type of image rejection receiver that is used in the RF system. So its main drawback is that it is very sensitive to the mismatches in the circuit. That is, if it is not properly matched, the part of the signals will be get reflected back to the source itself. So there will be some signal losses. So that the signal will not be properly delivered to the receiver. That is the main drawback if it is not properly matched. So uh, it's a main drawback is that it is very sensitive to the mismatches in the signal. That is, if the local oscillator signals are not exactly 90 degrees out of phase, okay? If the two signals are at a different gain or a different phase shift, the image cancellation becomes a very imperfect. So, yeah, in that condition, the 90-degree phase shift should be exact so that unwanted images cancels properly. So, if there is any imbalance, the receiver performance, I have already said that, right? So, the receiver performance reduces. So, next we are going to see for the Weaver architecture. In Weaver architecture, that is, the usual 90-degree phase shifter is replaced by the second quadrature mixing stage, which performs a similar functions of image rejection. So, the output signal is not centered at zero frequency. So, an additional secondary image problem appears to be second mixing process. To handle this, the low pass filters are replaced with band pass filters, which helps to suppress the secondary image and in order to improve the signal. So next we are going to see about the digital filter. In digital filter, this diagram shows the digital IF filter. where the signal is first processed in analog form and then it is converted to the digital form for final processing. First, the antenna and bandpass filter. The signal, the received RF signal from the antenna is very weak and it contains very unwanted signal. So, bandpass filter selects only the received frequency band. So, the mixture, second, it is passes to the mixer. That is a frequency down conversion. The signal is mixed with the local oscillator. That is a cos omega L naught T. This shifts the signal from RF to an intermediate frequency. That is a higher frequency. The main purpose is that easier filtering and processing at a lower frequency. Then it passes to the V.P.F. V.P.F is a higher bandpass filter. It removes the unwanted mixing products like image frequencies. It keeps only the desired radio signal. So next is IF amplifier. IF amplifier generally the amplifier used to boost the signal. That is, it is an amplifier is a weak signal, right? So it improves the higher signals from digitization. Then it is given to the ADC. ADC is the analog to digital converter. It converts the analog signal to the digital signal. And the digital processing section. Digital processing signal contains, that is a digital signal generator, and it will produces two reference signal, that is a cos omega t and sin omega t. That will be mixed with the digital mixtures, and that will be multiplied with the cos omega t and sin omega t. The cos omega t produces in phase, that is high component, and sin omega t that produces a Q component. Okay, right? So low pass filter. Low pass filter is a it removes the high frequencies and it allows the low rate of frequencies to pass through. That is the main principle, and it is explained briefly here. So subsampling receiver. Subsampling, that is, subsampling is a technique that is used to sample high frequency RF signal at very low sampling rate. That is the subsampling. And then the actual carrier frequency. The basic idea behind the subsampling is that the narrow band IF signal does not change significantly from one carrier to the next. So because of this property, it is always necessary to sample at the nyquist rate of the RF carrier. Instead, the signal can be sampled at a lower rate while still perceiving the required information. In subsampling, the high frequency RF signal is sampled at lower rate than the carrier frequency. One of the main advantages is that large reductions in the down conversion complexity. Okay, that is the main big advantage in subsampling receiver. The transmitter architecture. Transmitter, that is a RF transmitter, is a part of communication system that takes a baseband, that is a low frequency signals, and converts it to the high frequency RF signal. That is mainly suitable for the wireless transmission. The main functions of RF transmitter are modulation. That is, baseband signal is impressed onto the high frequency carrier signal. Then it is up conversion. That is, the modulated signal is shifted to the required carrier frequency using a mixture and local oscillator. Then power amplification, and it will be given to the receiver. So baseband RF interface. This diagram, that is a baseband signal. This is a original information signal. It is a low frequency signal that contains a message to be transmitted. Okay, then it is given to the signal conditioning block. Before applying the baseband signal to the VCO, it passes to the signal conditioning circuit. VCO is nothing but voltage controlled oscillator. Okay, this block mainly performs, that is a signal conditioning block, mainly performs the filtering, amplification, and scaling. What is the main use of filter? It removes the unwanted noise. Amplification, it adjusts the signals. Scaling is nothing but it ensures the correct modulation sensitivity. Then VCO. VCO is the key block in the system. It generates a carrier signal. This process reduces the frequency modulation directly, and the modulated signal will be that is the output will be get at the VCO, at the output of the VCO. And this is a explanation. That is minus 74. represent, this is the thermal noise flow density at room temperature. It is a constant. So that is a noise power in 1 hertz bandwidth. That is 10 log D represent that the increase in the noise power due to the system bandwidth. And that is a B is the bandwidth. And NF is a noise figure that measures how much noise the receiver adds compared to the ideal receiver. If the noise figure is very high, it's the sensitivity is very poor. Okay. Then SNR is a signal to noise ratio. Okay. Unwanted emission. Unwanted emission, that is unwanted emission refers to that is a part of a transmitted output signal that appears outside the assigned frequency band, especially in the adjacent channel due to the non-linearities and filtering imperfection. Thank you.